Good morning everybody. Today we deal with the nonlinear programming, especially about constrained quadratic programming. Now what exactly is the constrained programming problems are? Before we go into the actual session, we study about the nonlinear programming, especially with the quadratic programming constrained. Now here the instructional objectives are to demonstrate the nonlinear programming with the conditions that are involved in this one. The conditions are not linear but they are quadratic, and here after the session is over you should be able to define what is the nonlinear programming and you should be able to obtain the optimum solution. Optimum solution means either it could be maximum or minimum. Now here in this session we mainly use the concept of Lagrange's multipliers. The Lagrange's multipliers are used to optimize the given function. Optimize in the sense it could be maximum or it could be minimum also. Now here to formulate the problem we say L is defined as L of x1 x2 up to xn, lambda 1 lambda 2 up to lambda m is equal to f of the variables x1 x2 xn plus lambda 1 g1 that is the condition plus lambda 2 g2 that is the second constraint plus this is lambda m gm that is the m constraint. Now here lambda 1, lambda 2, lambda 3 so on, they are all called as the Lagrangian multipliers. In order to have these stationary values, we find out the partial derivatives with respect to all parameters that are involved in L and equate them to 0 to get a stationary value. First of all, when do we use the concept of Lagrangian multipliers? The Lagrangian multipliers, they are mainly used to find out the maxima or minima. When we say that it is optimization, it could be either maximum or it could be minimum. And Lagrange's multipliers is the most powerful tool for finding out the maxima or minima for the problem. Now how do we obtain? What is the mathematical formulation? We have got the function f and g. F is the original function where maxima or minima is to be evaluated subject to the condition. The condition is given on g. We say that the function, the original function f of xyz is equal to lambda times g of xyz subject to the conditions g of xyz is equal to k. Now better we illustrate with a problem here, that is f is given to be 5x minus 3y subject to the constraint, that is x square plus y square is 136. The original function is given to be as f of xy is equal to 5x minus 3y. F is the function that is defined with only two variables x and y. The constraint that is given as x square plus y square is equal to 136, which means that x square plus y square minus 136 that is equal to 0. That we call it as g of xy. Now here we define all partial derivatives of f with respect to x and y because there are only two variables. Similarly, the partial derivatives of g with respect to x and y because there are only two variables that are involved here. Now we apply the condition that the partial derivative of f with respect to x is equal to lambda times the partial derivative of g with respect to x. Similarly, the partial derivative of f with respect to y is equal to lambda times the partial derivative of g with respect to y. Now here such an equation is applicable which is dependent on the number of variables that are there in the problem. So especially in this particular case we get the equations 5 is equal to, this is 2 times lambda x, minus 3 is 2 times lambda y. We have got only one condition. What is the condition? The condition is x square plus y square is equal to 136. So using all these three, we get the value of x is 5 by 2 lambda and y is equal to minus 3 by 2 lambda. Out of all these things, lambda is equal to plus or minus 1 by 4. Ultimately, we need to find the value of lambda. So using this value of lambda, that is lambda is 1 by 4, we get x equal to 10 and y equal to minus 6. And similarly, when minus 1 by 4 is used for the value of lambda, the x is minus 10 and y is equal to 6. So using these values in the original function, f at minus 10 and 6, that is minus 68. F at 10 and minus 6, that is equal to 68. Out of these two things, minus 68 is minimum and 68 is maximum. So this is how we try to apply the Lagrangian multiplier and get the maxima and minima. The ultimate solution, whatever that is required, that we can take it, but the process is this. And here we take another example. Here we have got a box where the dimensions are length, width and height, they are x, y, z, and the volume is found to be x, y, z. That is the original function f. The total surface area is fixed. The box is closed. Therefore, it is 2 times xy plus yz plus zx, that is equal to 64. Because the box is closed on all sides. That means the condition is xy plus yz plus zx, that is equal to 32. So now what we need to do is, f is to be optimized subject to the condition. We have got only one condition, that is we call it as g. So as usual, the partial derivative of f with respect to x, y, z are to be obtained. Similarly, the partial derivatives of g with respect to x, y and z, they are to be obtained. And just like in the previous problem, we apply the conditions here. Delta f, or the partial derivative of f with respect to x, is equal to lambda times the partial derivative of g with respect to x. Similarly, the partial derivative of f with respect to y is lambda times the partial derivative of g with respect to y, and even for z also. Ultimately, the equations what we get is yz plus yz, zx and xy as given like this, subject to the constraints. That means the length, width and height, that is found to be 3.266. And here when we have got multiple constraints, g1, g2 and g3, all of them are equal to 0. So here we will be having the number of constraints more in number. So in order to illustrate this, we take a function f with 5 variables and we have got 2 conditions, x1 plus 2x2 plus x3 equal to 1, and the second condition is x3 minus 2x4 plus x5 equal to 6. The original function is called as f and the constraints are called as g1 and g2. So as usual, we find out the partial derivative of f with respect to x1, x2, x3, x4 and x5. And similarly, we apply the conditions, the partial derivative for g1, g2, g3 with respect to x1, x2, x3, x4 and x5. And we apply the same conditions just like the previous one. Now what we get finally is 2x1 plus lambda is 0, 2x2 plus 2 lambda 2, that is 0, and so on. Ultimately, we have got the 2 conditions, x1 plus 2x2 plus x3 equal to 1, and the second condition is x3 minus 2x4 plus x3 equal to 6. Solving for all these things, ultimately lambda is 0 and mu is minus 2, which gives us x1, x2 is 0, x3, x5 equal to 1 and x4 is equal to minus 2. That means the functional value is 6. So this is another illustration of applying the Lagrangian multiplier with more than one constraint. So this is how we try to apply the Lagrangian multiplier and try to get the values, and we take either the maximum or minimum, whatever that is required here. Thank you all.